All right, today we're going to tackle a really fundamental concept in power electronics, the single-phase full-wave rectifier. But we're not just going to stare at the textbook diagram. Oh no, we're going to dig into what really happens when you hook it up to a real-world inductive load and see how that messes with one of the most important numbers we care about, the power factor.
So, to really get a handle on the problem, we've got to start by picturing a perfect world. What does an ideal rectifier circuit actually look like when it's running? This is our baseline, the gold standard we're always trying to get back to.
Okay, so take a look here. In this perfect scenario, our load is just a simple resistor. Think of something like a toaster or a space heater. The current it pulls from the AC source, that's the orange wave, is a perfect rectified copy of the supply voltage, which is in blue. See that? They're perfectly in sync and they have the same basic shape. This means every single amp of current is doing useful work. And when you look at the numbers, it's beautiful. Zero harmonic distortion, a displacement factor of 1, and a perfect power factor of 1. Doesn't get any better than that.
But you and I both know the real world is almost never that clean and simple. We're not just powering toasters, we're running complex machines. So let's see what happens when we yank out that simple resistor and replace it with something way more common, like a DC motor.
You see, a DC motor, it needs a really smooth, steady, ripple-free current to run well. To get that, we put a big inductor in series with it. That inductor acts like a filter, smoothing out those bumpy pulses from the rectifier and giving us that nice, almost flat DC current you see labeled as I sub A. Now, this is absolutely fantastic for the motor's performance, but it creates a huge headache for the other side of the circuit.
And this right here highlights a classic trade-off in power electronics. The inductor is doing its job perfectly for the DC load, but by doing that, it completely changes how the rectifier pulls current from the AC supply. So what's good for the motor is about to become a major problem for the power grid.
So, what's the direct result of all this? What does this challenge for the AC source actually look like? Well, the main symptom is a complete and total change in the shape of the input current. So instead of drawing current in that nice, smooth sine wave we saw before, the rectifier is now forced to gulp down current in these sudden, choppy, almost square blocks. Just look at that mismatch. We have this beautiful, clean sinusoidal voltage from the wall, but the load is demanding this ugly, blocky, non-sinusoidal current. And that mismatch, that is the root of all our problems. So how on earth do we analyze a waveform that looks that messy? Our simple AC circuit rules, they just won't cut it here. We need a much more powerful tool, and that tool is Fourier analysis. It's kind of like a superpower that lets us break this ugly wave down into its simple building blocks.
So the magic of Fourier analysis tells us that our ugly square wave is really just a bunch of pure, simple sine waves all added together. There's one special piece, we call it the fundamental, that's the dashed line here, that has the exact same frequency as the voltage. Now, this is the only part of the current that does any real work. All the rest, we call those harmonics. They're just useless sine waves at higher frequencies that draw current and cause all sorts of problems, but they don't deliver any useful power to the load. Okay, so now that we get the problem in theory, we need a way to measure it. We're engineers, right? We need numbers. We need metrics to quantify just how bad this distortion actually is. So let's open up our diagnostic toolkit. First up, we have the displacement factor. This is probably the classic power factor you learned about in your first circuits class. It only looks at the timing difference, the phase shift, between the voltage and that one useful fundamental part of the current. It's all about when the current is drawn, not what shape it's in. The second, and for us, the really critical metric, is the harmonic factor. You'll also hear it called total harmonic distortion, or THD. This number directly measures the ugliness of the wave. It tells us exactly how much of the total current is made up of those useless, troublemaking harmonics compared to the good, fundamental part. So here's the crucial point. The real, true input power factor has to take both of these things into account. It's the master metric. It combines both the timing and the shape of the current to give us the full story of how effectively our circuit is using the power it's drawing. And this is the main thing I want you to take away today. The overall power factor isn't just about that phase shift anymore. It's the product of both displacement and distortion. So if your current waveform is full of those nasty harmonics, your power factor gets hammered, even if the timing is absolutely perfect. Those harmonics are a direct hit to your system's efficiency.
All right, that's enough theory. Let's get our hands dirty and apply this to a real example. We're going to analyze the rectifier-fed DC motor circuit from example 3.4 in our source material.
So here's the mission. We've got a standard single-phase bridge rectifier. It's feeding a highly inductive DC motor, and we know it draws a pretty much ripple-free current. Our job is to calculate two things. First, the harmonic factor, or THD, of the input current, and second, the final true input power factor.
Okay, the first step is to do a Fourier analysis on that square wave. Now, we're not going to grind through all the calculus here, but the results are what really matter. The analysis shows that the total RMS current, I sub s, is actually just its amplitude, I sub a. But more importantly, it tells us that the useful fundamental component, I sub s1, is only about 90% of that total.
Now for the easy part. We can just plug these values straight into our formula for harmonic factor. We swap in I sub a for the total current and 0.9 times I sub a for the fundamental. And as you can see, the I sub a terms just cancel right out, which leaves us with a really simple calculation. And whoa, look at that result. The total harmonic distortion is 48.43%. Just stop and think about what that really means for a second. Almost half of the current being pulled from the wall is made up of these non-working, wasteful harmonic frequencies. That is a massive amount of inefficiency. Okay, now for the grand finale, the overall power factor. First, we check the displacement factor. Because our square current wave is nice and symmetrical, it's in time with the voltage. There's no phase shift between the voltage and the fundamental current, so our displacement factor is a perfect 1.0. Then we just use our master formula to calculate the final power factor. And there it is. The final power factor is 0.9. Now, remember our perfect ideal case? That was a 1.0. We've lost 10% of our system's performance. And what's crazy is that it had absolutely nothing to do with timing or phase shift. The entire penalty is because of that ugly, distorted waveform.
So let's just step back and summarize what we've really learned here. This little case study shows in plain numbers the incredibly high price you pay for harmonic distortion in a power system.
I mean, this table says it all, doesn't it? The ideal resistive load, 0 THD, a displacement factor of 1, and a power factor of 1. Perfect. Our real-world motor, a staggering 48.43% THD. But look, its displacement factor is still a perfect 1.0. This means that the entire 10% drop in power factor, from 1.0 down to 0.9, is caused only by the distortion of the current. And this is why this is such a big deal outside of the classroom. These kinds of nonlinear loads inject what we call harmonic pollution back into the power grid, and that can mess with other equipment. Plus, all those useless harmonic currents are still flowing through real wires and real transformers, creating extra heat. That's I squared R loss, which is just wasted energy. All of this is the reason we have an entire field of engineering called power factor correction, or PFC, that's dedicated to fixing this exact problem.
Which really leaves us with the big final question, right? We've diagnosed the disease, and we've measured just how bad it is. We know these nonlinear loads are polluting our power systems. So how do we, as engineers, fight back? How do we design circuits that can clean up this mess and make that input current look like a nice, clean sine wave again? Well, that's the story for another time.
All right, welcome everyone. Today, we're going to dive into a really fundamental concept in power electronics. We're going to talk about why the current coming from a rectifier isn't always as clean as we'd like it to be, and, more importantly, how we measure the impact of all that distortion on the power system.
Okay, let's just jump right in. On the left, you see the dream scenario, right? A perfect, beautiful sinusoidal current. This is what you'd get with a simple resistive load. It's clean, it's smooth, it's predictable. But on the right, that's the reality for a lot of industrial loads. When we use a rectifier to power something with a lot of inductance, like a DC motor, the current it pulls from the supply gets twisted into that sharp, almost square-like shape. The difference is just night and day, and really understanding that distortion, that's our focus for this explainer.
Now, as engineers, we can't just look at that wave and say, yep, that's distorted. We've got to put a number on it. We need to quantify it. And to do that, we use a very specific set of tools. So let's break down the 3 key metrics we absolutely need to understand this problem. First up is the displacement factor, or DF. You've probably run into this one before. It's the classic power factor you learned about first. It's all about timing. It measures the phase angle, that's our little friend phi, between the supply voltage and the fundamental part of our current wave. It just tells us if the current is leading or lagging the voltage. Simple as that. Next, we've got the harmonic factor, or HF. Now, this one gets right to the heart of the distortion itself. It directly measures the jaggedness or the fuzziness of that wave. You can think of it as a ratio, really. It tells us how much energy is trapped in all those unwanted harmonic frequencies compared to the energy in the clean, fundamental frequency that we actually want to do the work. Okay, a super important point to lock in. Harmonic factor and total harmonic distortion, or THD, are just two different names for the exact same thing. They're a direct measure of the pollution on your waveform. So for a perfect sine wave with absolutely zero distortion, the THD is 0. And, just to be thorough, you'll also hear displacement factor called displacement power factor, or DPF. And that brings us to the big one, the true power factor, PF. This is the metric that tells the whole story. It combines both the timing issue, our displacement factor, and the waveform shape issue, our harmonic factor, all into one single number. This is the number that really matters at the end of the day, the one the utility companies are looking at. Theory is great, but let's see how this all plays out in the real world. We're going to get our hands dirty and analyze a super common scenario that you'll see all over the place, a full-wave bridge rectifier that's powering a DC motor. So here's our circuit. Pretty standard stuff, a single-phase bridge rectifier. But the key is the load, a DC motor, which is highly, highly inductive. Think of that huge inductance as a filter. It smooths out the current on the DC side, making that armature current, IA, almost perfectly constant, with no ripple. And it's that constant DC current that actually forces the AC input current, IS, to get chopped up into that ugly square-like shape. So how in the world do we analyze a messy, non-sinusoidal wave like this? Well, we bring out the big guns, the Fourier series. It's this incredible mathematical tool that lets us take any complex repeating wave, like our square wave, and break it down into a whole bunch of simple sine waves at different frequencies. We call those harmonics. So, the game plan here is pretty straightforward. First, we use the Fourier series to get a mathematical description of our square light current. Then, from that big equation, we pull out just the very first term, the fundamental component, IS1, and find its RMS value. And finally, we calculate the total RMS value of the entire current, IS, which includes the fundamental plus all those pesky harmonics. And after you run through all that math, you get this really neat and critical relationship. The RMS value of the useful fundamental part of the current, I sub 1, is exactly 90% of the DC armature current IA. Remember that number, 0.90? It's going to be super important in a minute. Now remember our assumption about that highly inductive load creating a perfect square wave? Well, because of that, the total RMS value of the input current, IS, is simply equal to the amplitude of that square wave. And what's that? It's just our DC armature current, IA. Okay, the moment of truth. We've got our RMS values for the fundamental current and for the total current. We have everything we need. Let's plug them into our formulas and see what shakes out. Let's see what the numbers actually tell us. Whoa, look at that. 48.43%. That is a huge amount of distortion. It means there's almost half as much energy sloshing around in those useless, noisy harmonics as there is in the fundamental frequency we actually want. This isn't just a number. This is a measure of the electrical noise this one device is injecting back into the power grid. Let's break this table down, because this is where it all comes together. First, check this out. Our displacement factor is a perfect 1.0. Why? Because the fundamental part of our current is perfectly in phase with the voltage, so no timing problem. But when we calculate the true power factor, which includes the distortion, we find it's only 0.90. That distortion has literally cost us 10% of our potential power efficiency. So what's the big picture here? What's the main lesson? Our displacement factor was perfect, a solid 1.0, but the overall power factor still dropped down to 0.9. Why did that happen? And here it is, the key takeaway. This is what it all boils down to. For that simple resistive load, you get a perfect power factor of 1.0. For a rectifier driving a motor, it drops to 0.9. And the entire reason for that drop is the harmonic distortion. It wasn't a phase shift problem, it was a shape problem. The waveform itself was the culprit. And this leaves us with a pretty massive question to think about. We just looked at the effect of one single motor. But think about our world today. These kinds of rectifiers are everywhere. They're in your computer, your phone charger, in electric cars, in factories. So what's the cumulative effect of all this electrical noise from millions and millions of devices on the stability and the health of our entire power grid?